Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 8, Applying Chemical Ideas, Inquiry Question 2, Analysis of Organic Substances. We're going to be focusing on carbon-13 nuclear magnetic resonance. So this is quite similar to what we talked about last lesson with the proton version of this, but we are going to just quickly recap on the interpretations if we're using carbon-13 instead of protons. Again, as always, that is your textbook reference if you want to do further reading. We talked about before when interpreting the spectra for resonance, the number of specific peaks will tell you the specific types of environments. The intensity of the peak or the amount of peaks will tell you the functional groups potentially in your spectra. And obviously the little mini peaks you see from your main peak will also tell you the number of hydrogens in a given environment that we have here. So in our third environment, we are expecting to have 3 hydrogens, as you can see, like so. One of the things I did not mention in last lesson was this concept of spin-spin coupling. So we can have a scenario where we have our usual spectra, but depending on the way in which the magnetic field is applied, we can actually split that spectra into 2 or 3 or even more little peaks from what we actually initially expected. So this splitting observation tells the type of magnetic interactions between the adjacent hydrogens. We call this spin-spin coupling. Now, spin-spin coupling describes any interaction or magnetic interaction with neighboring non-equivalent active nuclei. When we mean by non-equivalent, we mean the hydrogens that aren't within the same type of environment. So you can see that these two are in the same environment, while this hydrogen is in a different environment. It can tell us how they interact with the magnetic field and also with each other in that sense there. So I guess the thing we need to talk about is how can we tell how it's interacting. So in addition to shielding by valence electrons, as you know, the shielding effect of valence electrons will mean that they will absorb some of the radio waves. If we use HA, or the alpha hydrogen as the example, let's say it's influenced by a small magnetic field by HB. Because remember, if we're dealing with an odd number of protons and neutrons, they will have spin. So if they have spin, they will also generate their own magnetic field there. So, well, not carbon-13, but hydrogen will have spin. And so if it has spin, it will also have its own magnetic field. So that's the interaction that they're getting there. Now, say for example, the hydrogen B example that we have aligns with the magnetic field that we're producing. So hydrogen B, it aligns, so it's moving in the same direction at which I'm applying my B field. So the B field is going in this direction here. Okay? What will happen if it's spinning aligns with the magnetic field? It causes the hydrogen A to be de-shielded. So it de-shields some way the radiation of hydrogen A, so that's more radiation that goes in, causes splitting. If it goes the other way, if HB opposes the magnetic field, so maybe it goes in this direction, then it actually shields the hydrogen A from interacting with any radiation. So that's just sort of a little thing that you can take into account for as well, but it's not a big part of what you need to know, because as a matter of fact, they do want you to more know how to use all 3 of these all together. Okay, so let's look into carbon-13 magnetic resonance. So just a quick recap, we said that the purpose of magnetic resonance is to find out the number of particular types of atomic nuclei in the substance. So this is what we can see here. It is used to determine the structure of the molecule, so we want to use it like that. But obviously if you want to work out the functional groups, so if you want to work out the functional groups, you will need to use other things such as infrared spectra. Now that's a lot more accurate in terms of working out specific functional groups. This one will just tell you sort of the main chain of the structure. We also said the reason why it works is because when we use odd numbers of protons and neutrons, in this case carbon-13, which has 6 protons and 7 neutrons, it will have a property called spin, and when we put it in a magnetic field, it'll cause it to align with that magnetic field. In that situation, we can actually make the magnetic component or the magnetic field of the charged particle to rotate in a particular direction by adding in radio waves. So if I have a particular magnet and I add in radio waves, it's going to cause it to rotate in an orientation that is opposing the alignment of its magnetic field. So in this case, if this side was south, this side was north, once it's absorbed that radio wave, this side flips over with each other, and that gives it a higher energy. So that's high energy. And we said that if it's just aligned with the magnetic field, we say it's low energy. So this one is aligned, this one is opposed. Okay, and then obviously we said what the choices were. We said hydrogen 1, which is basically a proton, and then carbon-13. Those are odd number nuclei that we can use for this type of spectra. As I said before, if we rotate it to make it oppose the magnetic field, then we'll be at a higher energy state, and if we just align with the magnetic field, then we are at a low energy state. Okay, so the next thing we need to do is look at interpreting carbon-13 spectra. Same idea as always. We have the chemical shift that we talked about before, so I won't go through it again. We did talk about the carbon environment, so working out what the carbons are aligned to. That will tell us how many different environment types that we have. And do remember when we talk about chemical shift, these interactions are based on the magnetic field strength or the radiation resonant frequency we use. So there is a specific range. This will tell you the different types of carbon bonds and also the different hydrogen bonds, but obviously there are multiple different types of functional groups that aren't just based on these carbon components here. So obviously you will need additional spectras to help you out with that. So let's have a look with a structure like so here. We have our little ester alcohol groups here. You can see if I just was to count the different types of carbon groups, I have 1, 2, 3, 4, 5 different carbon environments. So as you can see here, I see 5 specific carbon or peaks. And if you know which specific resonance are you using, so hydrogen or carbon, you can actually use the formula sheet or data sheet to actually specifically look at which shifts are you seeing on this chart here. So it's very useful. This is in your formula sheet, so you can find this. I also like to quickly thank the teachers of Rose Bay for allowing me to use this slide for this particular presentation, so thank you very much. Okay, so when it comes to interpreting carbon-13 spectra, the location will indicate whether or not there's been shielding or deshielding, and it also tells us the type of carbon molecule that's being contained. Obviously, different types of carbon bonds will have different types of chemical shifts. Okay, so maybe I'll just put that as an extra. So location peaks is that each type of carbon environment has a specific chemical shift. And so if I know what the chemical shifts are, I can work out the type of carbon bond that I'm dealing with here. Obviously, the number of peaks will indicate the number of carbon environments possible. In this case, or in this chart that I have here, I'm expecting 2 types of carbon environments, and then this will show me sort of the kind of bonds within that carbon group or carbon environment. Let's have a look at this question here just in terms of how to interpret it, and then obviously you can have a go at some past paper questions that can help you with that. So we have this particular molecule here, as you recall, that is an aldehyde. So if you recall, with our aldehyde we have 2 carbons, 1 carbon is bonded to 3 hydrogens, and this carbon here is bonded to a hydrogen and also bonded to an oxygen. Okay, now let's quickly look at the type of scenarios that we have. So this carbon here, let's call it environment 1. It's bonded to a hydrogen, 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 and a carbon. So that's the environment that we have here for this one. If we look at our other carbon, it's bonded to a hydrogen. So far, similar to our first one, it's bonded to a hydrogen. So carbon to carbon, carbon to hydrogen. So far, that's quite similar to what we originally had, but this carbon is also bonded to an oxygen. So it's bonded to something that's different to what carbon 1 is. So this is actually the second carbon environment. So we expect 2 carbon environments. So 2 environments, which means we should also expect 2 carbon peaks in our resonance structure there. In terms of shifts expected, you can see the chart that I've given you. We have the CH bond, so we have the alkane group, and then obviously we need to work out the other components there. Alright, so you might see here we have a slightly different table. Just had to do a little bit of editing on the go because I realized the table I used was for the hydrogen resonance spectra, but we are dealing with carbon, so we got to use this one here. So the function group that we're seeing is our CH3 bonded to an alkane group. So if I look at what my chart is showing me, I should see a chemical shift of 8 to 25 parts per million. That's what I should see. And then for my component here, where I have an aldehyde, according to the chemical shift that I should expect here is 190 to 100 or 200 parts per a million. Okay, so you have these 2 parts here. Alright, so those are the 2 expected chemical shifts I should have. Let's check the answers. Hopefully I'm not wrong. And there you go. So that's the answer there. Alright, so I know you might think this is a relatively short recording, but obviously short and sharp is always nice. So that kind of concludes our topic about the carbon nuclear magnetic resonance, and that concludes everything we've done for Module 8, Inquiry 2. We've looked at different techniques to examine the different types of organic chemicals, organic compounds. But remember, when it comes to infrared spectra, mass spectra, and then obviously lastly our resonance, each and every one has their own specific points where they're better than the other. Infrared is great for functional groups. Mass spectra is great for knowing the molecular mass. Nuclear resonance is really good at telling you the different carbon or hydrogen environments, but obviously there are limitations to all of them. You can't really make a specific conclusion with just one. You do need to know, use all three of these to actually come up with a conclusion of the structure. So in actual fact, in organic chemistry, we actually use all three techniques to look at the one molecule. And that's the kind of level of understanding you need to know to succeed in HSC chemistry, because a lot of late questions in the current trend is to test your skills at observing these types of spectras. Alright, so I hope you found this module interesting. I hope you found this inquiry interesting. And if you find these videos that I'm making are quite useful and interesting, give a like, show a bit of love and support. And till the next recording, have a nice day and stay safe.